Welcome back. So what are the most important hyperparameters in the decision tree? First, we have the criterion. Okay, the default criterion is the Gini criterion, and this hyperparameter is important because based on this hyperparameter, we will choose the attributes. We will choose the attributes and we will choose the values in the decision tree. And we can choose one of two criterion. We can choose Gini for Gini index, or we can choose entropy for the information gain. So what is the difference between Gini and entropy? The Gini impurity measures the frequency at which any element of the dataset will be mislabeled when it's randomly labeled. Okay, so this is how the impurity works. So it's calculated as follows. So it's calculated using this equation, 1 minus the summation of probability square. So the Gini index has values inside the interval between 0 and 0.5, while on the other hand we saw that the interval for the entropy is from 0 to 1. So this is the first difference between entropy and Gini index. And then the second difference between the entropy and Gini index is that entropy is more complex computationally because it makes use of logarithms, right? Of logs. We had a logarithm in the equation of the entropy, right? And when we implemented it, we used numpy.log, right? On the other hand, for the Gini index, we don't really have any logarithms. We are just calculating the squares, right? And summations. So computationally, it will run faster than the entropy, okay? Because the logarithm is actually computationally intensive. So these are the most important, or these are the two differences between Gini and entropy. And you can try this and try this, but in terms of the accuracy, both of them will give you very, very similar results. But if you care about the computational speed, then you might choose the Gini index. But it's a little bit confusing to understand, okay? The entropy and information gain idea is much easier to comprehend and to understand. So this is the first criteria, or the first hyperparameter. And then we also have the splitter. Okay, so this is a string and it can be either best or random. This is the splitting strategy. So this parameter allows us to choose the split strategy. The supported strategies in sklearn are best, so this will choose the best split, and this is the strategy we choose actually when we implemented the algorithm ourselves, right? But random is more efficient because it will choose the best random split. So instead of looking at all the values, which might be very, very computationally intensive if we have a lot of unique values, the best strategy will not be that efficient. On the other hand, the random strategy is much more efficient because it will choose, for example, 100 random samples, okay, and it will take the best out of these 100. Okay, so the maximum number of values it will need to look at is 100. But if we choose the best as our strategy, then it will be much more than 100. Okay, the third hyperparameter, we saw it already, was the maximum depth. And by default in sklearn, it's none, so we don't really have any maximum depth of the tree. It will continue until we classify all of them correctly. Okay, so if none, the nodes are expanded until all the leaves contain less than minimum samples split samples. So this is actually another hyperparameter. If it's 1, then it's basically a leaf with one node. And it makes sense that if we set a higher value for the maximum depth, then this will cause overfitting, okay? And if we choose a lower value for the maximum depth, then this will cause underfitting. Underfitting means the training accuracy is very low. The model is not really fitting the data, and overfitting means is that it's even fitting the noise. So when we are seeing the training versus the testing accuracy, the testing accuracy is much less than the training accuracy. So this is an indicator of overfitting. After that, we have the minimum samples per split, right? So this is the one we were discussing here. So the minimum number of splits, or minimum samples to split, is the minimum number of samples required to split an internal node. So we can choose this to be 10. So for example, if we go to the graph, you will see that each time we have a number of samples for each node. So we can set this to be, for example, 100. So if we reach the node that contains 100 samples, then we will stop, even if we didn't reach the maximum depth. Okay, and then we have a very important hyperparameter called class weight. So this is a dictionary, okay, a list of dictionary or balanced. So if we choose balanced, then this means that we want to check the data, we want sklearn to check the data for us and see how the labels are distributed and give a weight for each class based on how well it's represented. Okay, and we can force this weight ourselves using a dictionary. So we will have in this dictionary, for the first class we want a weight of 0.9, and for the second class we want a weight of 0.1. okay, and the default is of course none. So if we didn't really specify a class weight, then sklearn will treat them equally. Okay, now these are the most important hyperparameters for the decision tree. But does this mean that these are the only hyperparameters? No. If you go to the tree and create a new object of the decision tree classifier, you will see that we have the criterion, the splitter, the maximum depth, the minimum samples per split, the minimum samples per leaf. We can have also minimum samples per leaf, right? We can have maximum features to split based on. We can have the random state to reproduce our results, the maximum leaves per nodes, right? We want a maximum leaves per node. The minimum impurity decrease, for example, if we want to stop if the entropy is decreasing by 0.001, right? If it's 0.001 or less, then we can stop. The minimum impurity split, the class weight, and we have also pre-sorted. Okay, and this is actually not used anymore. So these are the most important hyperparameters. And we have one final hyperparameter here that we are going to discuss in a future lesson called CCB alpha. And by default, it's 0.0. Okay, it's 0, right? So in the next lesson, when we are talking about pruning, you will see this hyperparameter used and we will understand what this hyperparameter is for. Now let's perform hyperparameter tuning, right? So here we are creating the decision tree classifier with the criterion as entropy. So this is the actual classifier or the initial classifier or the default classifier. And here we have a dictionary containing either the criterion to be Gini or entropy and the maximum depth from 3 to 9. Okay, so we will try all different combinations using Gini, entropy, 3 to 9 for the maximum depth. Okay, so how we are going to do this? We are going to do this using the grid search. Okay, so the grid search cross validator, what it will do is that it will basically take this classifier and it will take the parameter grid. Okay, and this class is from sklearn, right? So it will perform exhaustive search over specific parameter values for an estimator. Okay, and we will do this using the fit function. So it will try to fit the data using all combinations for our hyperparameters. So we will give it this dictionary and it will start by fitting Gini with a maximum depth of 3, and then Gini with 4, Gini with 5, Gini with 6, Gini with 7, Gini with 8, and the same for entropy, right? And it will give us the best results. Okay, so why we are having a loop here from 3 to 6? If we run this, you will see here a bar, a progress bar, right? And it's saying start fitting the data, right? And now it was 1, now it's 2, and this is the time left, the time elapsed and the time left, right? And the score for threefold CV is 0.95, and this is the best result, and here 4-fold CV and here 5-fold CV. So what we are doing is that I am using the grid search with this hyperparameters grid, right? And I am also specifying how many folds I want to use, right? So if you remember in the KNN, we discussed the idea of k-folds, right? So if we want to have a k-fold of 3, then we will just insert here 5, 4, 3, 2, 1, depending on how many k's we want, how many folds we want, right? So we will try with 3 folds, 4 folds, and 5 folds, right? And the maximum depth, by the way, here is 8, right? Because 9 will not be included. And we will use the fit function, right? And basically this taqaddum is a library we imported in the very beginning, right? To have this very nice progress bar, and in order to see how much time elapsed and how much time left. So it's pretty nice, right? So here we created the grid search. Here we are using the fit function, and here we use the score. So from the grid we use the score to get the score between the X test included and the Y test. So this will give us the score, okay, the best result we can get. And what are the best hyperparameters? So we got here 0.856. So we got this using a criterion of entropy and the maximum depth of 7. And then we got even better accuracy, right, by 0.1 using a Gini and a maximum depth of 8, right? So we increased the accuracy by nearly 1.5% from the default decision tree, right? So this is how we can perform hyperparameter tuning the most efficient and the easiest way. Now in the next lesson we will start discussing how we can avoid overfitting in decision trees and why we might have overfitting in our decision trees, and then we will discuss pruning, which is one of the most efficient ways to avoid or to decrease overfitting in decision trees, and we will see the hyperparameter called alpha, which we mentioned a few minutes ago. So let's go to the next lesson.